We are going to begin Chapter 8, which is on confidence intervals today. And I have a few definitions I want to talk to you about, and some of these have specific wording that I want to make sure that you have down. I usually start this lesson out with my students in person and talk to them about the importance of communication when you're writing. When you are writing your answers to free response questions, you are trying to show everything that you possibly can show that you know about a topic to the reader. And the reader or grader doesn't know you. And so you have to make sure that you are communicating as clearly as possible that you understand how to do these different procedures, especially when we get to inference procedures. And the first inference procedure that we're talking about here is confidence intervals. So I'm going to go over some steps that will help to make sure that you are completely covering all parts of that. And that's going to be something that we want to make sure that we're very thorough on from here on out during all of these different inference procedures. Okay, so a couple of definitions. And the first definition is called the point estimator. And that's a statistic that provides an estimate of the population parameter. And we've been doing this so far. In Chapter 7, we talked about, even back to Chapter 4, when we take samples and we find that X-bar or that p-hat from that sample, that would be my point estimator. That's what I'm using to try to estimate what's going on with the true parameter, mu or p. So the value of that statistic, that X-bar or that p-hat, is also called a point estimate. Okay, so point estimator or point estimate. So the point estimator is X-bar p-hat. The specific number that you get is called the point estimate. Now, when you are creating a confidence interval, that point estimate is your beginning point. I start with that point estimate. Now, we've talked in the past about when I take a sample, you have sampling variability, correct? There are lots of different results that can come if I take different samples. If I take a sample of size 50 from a population, let's say the population is Lincoln High School students. If I take a sample of size 50 and I'm interested in the proportion who go off campus for lunch, if I take another sample of size 50 from that same population, I might get a different p-hat. And that's okay because I have different people in the sample and I expect that variability. So what kind of accounts for that variability is something called the margin of error. And sometimes you'll see me just write ME for margin of error. Okay, so a C% confidence interval, and we might do a 95%, we might do a 90%. It's stating how confident we are in our results, which we'll get to in a second. A C% confidence interval gives an interval of plausible values for a parameter. Not possible, but plausible. Okay? Plausible values for a parameter. Means believable. Makes sense, right? The interval is calculated from the data and has the form, start with the point estimate, plus or minus the margin of error. The difference between the point estimate and the true parameter value will be less than the margin of error in C% of all samples. All right? That confidence level. That C there, that's the confidence level. The confidence level gives the overall success rate of the method for calculating the confidence interval. That is, in C% of all possible samples, the method would yield an interval that captures the true parameter value. Now, let's stop right here for a second. That confidence level is not how confident I am in a specific interval. Okay? Be careful about that. Do not tie that confidence level to how confident you are in a specific interval. Instead, it's how confident I am in the process used to create that interval. If I am constructing a 95% confidence interval, what that's saying is that if I were to construct this interval over and over and over again, 95% of the intervals I constructed using this method would give me intervals containing the truth. That means 5% of the time, I'm going to have intervals that don't. Okay? So it's very important to understand that confidence level is tied to the method you're using. That's how confident you are in the method used to create that interval, not tied to a specific interval itself. Okay? So let's put this a little bit in context to kind of talk about the different parts real quick. So If I were trying to estimate the IQ level of a certain student, or of a group of students, let's say I wanted to know the average IQ of my AP Stat students, and I constructed a 95% confidence interval, and I told you, okay, here are my results. I have a 95% confidence interval of 127 plus or minus 5. What that means is I have an interval from, well, 127 minus 5, that would be down to 122. And 127 plus 5, that would be up to 132. So my 95% confidence interval would be this right here. And you can write intervals out as this, separate, the point estimate and the margin of error separate, or as an actual interval like this. Okay, so the 5 is representing my margin of error. Now, more specifically, let's talk about what this represents. Go back to, in your brain, chapter 2, when we talked about looking at a normal curve. When I'm constructing a 95% confidence interval, what that's doing is it's giving me the middle 95%. So essentially, that 5 is representing 2 standard deviations on either side of my point estimate, right? Okay. And if I were doing 90%, that would be the middle 90%, okay? Would we get 127 with every sample? If I took another sample of AP Stat students and found the average IQ score, would I be guaranteed to get 127 again? No. And in fact, my range might look much different. Now, if I'm sticking with the same confidence level, my margin of error will not change. So I'll have different widths. In fact, as I am collecting these, if I were to do lots of examples, let's say this line right here represents the true mean IQ score. Okay, and this is unknown to me, right? I don't know what it is, but let's pretend it's like 125. Okay, well, the interval I just calculated was from 122 to 132. Did that capture the truth? Yeah, it did. But let's say the next one I get is from like 120 to 130. Well, that would also capture it, wouldn't it? And so what might happen is as I take samples, since I'm 95% confident, as I take different samples, they may vary, right? My width will be the same on all of them. But 95% of the time, these samples and the intervals that I'm constructing from these would give me an interval that captures the truth. Now, that means 5% of the time, though, I may end up with an interval that doesn't capture the truth, right? Okay, so that's something to keep in mind. All right, so essentially here, 127 is our X bar. Sorry, I forgot the bar. It's the average, plus or minus the margin of error. And that would change depending on the sample. All right, let's talk about interpretations. And these are two that you definitely want to have written down. These are really important statements that we need to make. When we create confidence intervals, at the end, we will be making a statement interpreting that confidence interval. And so this right here, this statement right here, is the conclusion that we're going to draw at the end of creating the confidence interval. And so this is going to be an important statement we want to make. So to interpret a C% confidence interval for an unknown parameter, say, and here it is, we are blank percent confident, whatever the confidence level is, that the interval from blank to blank captures the actual value of, and then you're going to state the population parameter in context. So you got some blanks to fill in. You got to fill in the percent here, what the actual interval was, and what you were trying to capture. If I go back to my example from before, if I wanted to interpret this interval right here using this statement, I would say we are 95% confident that the interval from 122 to 132 captures the true mean IQ score of AP Stat students. See how I included the confidence level, I included what the interval was, and what I was trying to capture. The whole purpose of a confidence interval is to try to capture the truth, either the true mean or the true proportion. Now remember, this is a much better estimate of what's going on than just one single sample and looking at just one stat, right? Because if you remember from before, that stat is going to vary because of sampling variability, right? But that margin of error then gives us a little wiggle room. And so calculating a confidence interval on a sample is a much better way of trying to estimate where the true parameter is. Okay? So this is an important statement to make sure that you have down, because that's going to be your conclusion you draw every time you create an interval. Now, another important thing to understand is what the confidence level is telling us. And I touched on this a little bit earlier. But the confidence level, here's what it means. In that last example, I used 95% confidence. To say we're 95% confident is shorthand for if we take many, many samples of the same size from this population, about 95% of them will result in an interval that captures the actual parameter value. That means if we take many, many, many samples of the same size, 5% of them, or about 5% of them, will result in an interval that does not capture the actual parameter value. Okay? Again, that level of confidence is how confident we are in the process, not in a specific interval. Okay? And here it is again. Confidence level does not tell us the chance that a particular confidence interval captures the population parameter. It's not tied to a specific interval. Instead, it's tied to the process. It's how likely it is that that method or that process would produce an interval that captures the truth. Okay? It's giving us a list of plausible values for the parameter. So be very careful about that. All right, let's see if we can try a couple and understand what's going on here. All right, so how much does the fat content of brand X hot dogs vary? To find out, researchers measure the fat content in grams of a random sample of 10 brand X hot dogs. A 95% confidence interval for the population standard deviation is from 2.84 to 7.55. Interpret the confidence interval. Okay, so let's go back to our statement. Pull that statement back up right here. And I want to interpret the confidence interval. So I'm going to use this statement right here. So we are 95% confident that the interval from 2.84 to 7.55 captures, now what were we trying to capture? We were trying to find how much they vary, and we were doing it with the standard deviation. So we are 95% confident that the interval from 2.84 to 7.55 captures the true standard deviation in the fat content of these brand X hot dogs. Okay. Interpret the confidence level. All right, well, we're going to talk about right here, right? If we take many, many, many samples of the same size, so if we take many, many samples of size 10 of these brand X hot dogs, and we create intervals over and over and over again, about 95% of those intervals will capture the actual parameter value. Again, that 95% is not tied to this specific interval. Instead, it's tied to the process used to create this interval. So to interpret the confidence level, if I were to take many, many, many samples over and over and over again, about 95% of them would capture the true standard deviation that I'm trying to find. All right, and the last one here, true or false? The interval from 2.84 to 7.55 has a 95% chance of containing the actual population standard deviation. Okay, what did we just say? Is that 95% tied to the specific interval? No, this is false. There is not a 95% chance of it being in this interval. The 95% chance is not tied to a specific interval. Rather, it is tied to how confident we are in the process used to create that interval. Okay. Let's talk about a little bit more specifically what our confidence intervals, are going to contain. Now, if you have your formula sheet in front of you, you will see that this wording right here is on your formula sheet right here. Okay, so if you look at your formula sheet that I gave you at the beginning of the year, down at the bottom it says confidence interval. Your statistic, so it's either going to be, for us, we're only doing confidence intervals on means and proportions. So if it's a mean, it's going to be X bar. If it's proportions, it's going to be P hat. Plus or minus your critical value. Now, your critical value is representing the number of standard deviations away from the mean you are. Okay? Now, for right now, for us, the only way we have learned to measure that is with z-scores. We are going to learn a different critical value when we talk about means, but we'll get to that later in the chapter. It's called t. Okay, so critical value is either going to be z or t, but we'll talk about t later. And then your standard error of your statistic. Okay, standard error. If you flip your paper over, notice how, do you see how on these tables we have the parameters of sampling distributions, and you have your standard deviation, mean and standard deviation for each of these, mean and standard deviation. But then over here it says standard error of a sample statistic. Here are your standard errors right here. Now what's a standard error? Well, a standard error is honestly just your standard deviation, but it's calculated using the statistic because we don't know the true parameter. Okay, so standard error is essentially just your standard deviation, but it's using the statistic to estimate it instead of the parameter because we generally don't know the true parameter. Okay, notice how, like coming out here, the means. The standard deviation was the population standard deviation of the square root of n. The standard error is the sample standard deviation over the square root of n. See how all the difference was that we substituted the sample standard deviation in? For proportions, instead of p's, we use p hats in the calculation of the standard deviation. So standard error is just the standard deviation using a statistic in place of the parameter because we don't know it. Okay, so again, here is the form we're going to see when we create confidence intervals. You're going to start with your statistic. That's either going to be x bar or p hat, depending on whether we're dealing with means or proportions. Then plus or minus your critical value. Now, that's either going to be t or z. We haven't learned t yet. That's going to go with means, but we'll talk about that later. And it's just a number of standard deviations away from the mean. And then the standard deviation of your statistic, or standard error, is what we call that. Okay? And those standard errors, again, are found right here. Standard error for proportions, right there. Standard error for means is right there. Okay? For one sample. Two samples down here, but that's another chapter. Okay? All right. Now, if I am doing a 95% confidence interval, if we go back to the example I gave you with IQ scores, I started out with an IQ of, now I've forgotten what it was. Was it 127? So that was my mean, right? Plus or minus. Okay. That 95% is going to help me find that critical value. That's where this comes in. Okay, remember it's the middle 95%. Well, we know from the empirical rule 68, 95, 99.7 that the middle 95% is 2 standard deviations away from the mean, right? So that's where that 2 comes in. And then times whatever the standard deviation of that mean is, and that would give me my margin of error. So 2 standard deviations away, so 2 times standard deviation would give me that margin of error. It would give me the middle 95% range. Okay? And that's how we calculated that. Okay? Okay, so let's kind of apply this a little bit. All right, a consumer watchdog organization estimates the mean weight of 1 ounce fun-sized candy bars to see if customers are getting the full value for their money. A random sample of 25 bars is selected and weighed, and the organization reports a 90% confidence interval for the true mean weight of the candy bars is 0.992 to 0.998 ounces. Okay, so we have this interval, this 90% confidence interval, from 0.992 to 0.998. Now the first question asks, what is the point estimate from the sample? Well, where is the point estimate found? If you think back, remember when we looked at the original setup of a confidence interval, your point estimate was your statistic, correct? And it should be right in the middle between where I added and subtracted, correct? So it should be right in between these two right here. So could I find the number that's right between these two? I could do 2 different things. I could just look at this and see what's right in between. Or I could add the 2 together and divide by 2, right? Either way. Right in the middle of these 2 would be 0.995. And so that would be the point estimate. That meant when we took this sample, the average size of the 25 bars was 0.995 ounces. Now, what's the margin of error? Well, remember, our formula, we have a statistic plus or minus your margin of error to create the interval, right? So what did I have to add to get to this number, and what did I have to subtract to get to this number from this point estimate? Well, that would be 0.003, right? So essentially, to get this interval, I could deconstruct this to find the beginning point, right, the middle point, which is a point estimate. And then I can see what the margin of error was then, the distance to either side. Or you could have just subtracted the difference between the highest and lowest and divided by 2, right? Either way. Okay? All right, now let's practice interpreting again. Interpret the 90% confidence interval, 0.992 to 0.998 in the context of this problem. All right, let's go back to our statement. And I'm going to bring this statement back up again and again and again and again until you have it completely memorized. In fact, this is a statement that you will want to memorize. Okay? So I'm going to just rewrite this statement right here. We are 90% confident that the interval from 0.992 to 0.998 captures the true value of, what am I trying to find? I'm trying to find the mean weight of 1 ounce fun size candy bars. So we are 90% confident that the interval from 0.992 to 0.998 captures the true mean weight of 1 ounce fun size candy bars. Okay? Interpret the confidence level of 90% in the context. Okay, is that 90% how confident I am in this specific interval? No. It's how confident I am in the process used to create this. What I'm saying, if I am 90% confident, that's saying if I were to use this process over and over and over again and take lots and lots of different samples and calculate lots and lots of different intervals, 90% of the intervals constructed using this method would create intervals that capture the true mean weight of these fun-sized candy bars. That means 10% of them would not. Good. All right, let's try another one. Young people have a better chance of full-time employment and good wages if they're good with numbers. How strong are the quantitative skills of young Americans of working age? One source of data is the National Assessment of Educational Progress Young Adult Literacy Assessment Survey, which is based on a nationwide probability sample of households. The NAEP survey includes a short test of quantitative skills covering mainly basic arithmetic and the ability to apply it to realistic problems. Scores on the test range from 0 to 500. For example, a person who scores 233 can add amounts of 2 checks appearing on a bank deposit slip. Someone scoring a 325 can determine the price of a meal from a menu, and a person scoring 375 can transform a price in cents per ounce into dollars per pound. Suppose you give the NAEP test to a simple random sample of 840 people from a large population in which the scores have a mean of 280 and a standard deviation of 60. The mean of this 840 scores will vary if you take repeated samples. Sorry, ran out of room on here. I had to go to the next page. All right, describe the shape, center, and spread of the sampling distribution of X bar. Okay, so we aren't done with Chapter 7 yet. We've got to still keep Chapter 7 in our brains because we're going to use this now. Okay? All right, so the shape